This is a good one. I'm sure this is going to take more than one video to cover this whole topic. The calculations got a little deep, but they're fun. This is change of variables in multiple integrals. So in Calc 1, probably at the end of Calc 1, you did U substitution, where you took a region and you changed those limits of integration to make it an easier function to integrate. Well, here we're going to do something similar, except what we're really focused on now is trying to make that region a nice region to integrate. Right? Rather than one of those regions that are defined by multiple functions or maybe impossible to set up a boundary on the base for, if we can turn that into a rectangle, that's a whole lot easier. So now we're changing the area over which the surface is being integrated. Generally, we use U's and V's as the new region's variable. So we're going to look at this a couple of different ways. I'm going to start with a couple of examples where we just look at the original functions. Like if I give you things in terms of x and y, can you put them into u's? If I give you things in terms of u, can you put them back into x's and y's to see how these things work? All right, so consider this unit square. How can we find the image of that unit square in the xy plane under this transformation? That that x is equal to 2u, and that y is equal to v over 2. So in the uv world, right, where the two axes are u and v, this is just one unit this way, one unit that way. That's why they call it the unit square. It's a square that's a unit on every side. Where did that come from in the xy plane? Well, if x is equal to 2u, and I divide both sides by 2, then x over 2 is equal to u. Well, u, the problem up on top here says the u's went from 0 to 1. So replace that u with an x over 2, and x over 2 goes from 0 to 1. Multiply everything through by 2, and I get 0 less than or equal to x less than or equal to 2. So in the xy plane, the x's went from 0 to 2. Okay. How about the y's? Well, here it says y is equal to v over 2. If I multiply both sides by 2, then I'll get 2y is equal to v. Well, again, over here, because it's a unit square, the v's went from 0 to 1. Replace that v with a 2y, and divide. So I get 0 less than or equal to y less than or equal to a half. Right, so this was the original rectangle in the xy plane, and by using that transformation, we were able to transform it into a unit square on the UV plane. All right, not so bad so far. Let's take a look at something a little bit more complicated. So consider that same unit square, except now I've got a different set of substitutions. The previous one wasn't so bad because I could get u by itself and I can get v by itself and x and y easily. This one, I've got u's and v's mixed together in both of these transformations. So what is the image of that unit square in the xy plane? In other words, what was it before I turned it into a nice, easy unit square to evaluate? So let's walk around that UV rectangle. What does the UV rectangle look like? Well, it's really a square, but every square is also a rectangle. So this is the u-axis. Here's u equals 1, v equals 0. Here's u equals 1, v equals 1. Here's u equals 0, v equals 1. And here's the origin, 0, 0. So the first thing is, let's walk across the bottom. If I walk across the bottom over here, where am I going? I'm going from u equals 0 to u equals 1. So I'm going from u equals 0 to u equals 1. The v values are 0. So that must mean that when x is equal to 0, y is equal to u squared. How do I know? Go back up here. Y is u squared minus v squared. Well, if v is 0, y is u squared. All right, let's look at the left side. what's happening to the u values? The u values are 0. The v values are going from 0 to 1. So again, if I come back here, the x-coordinate is still 0. On the other side, if I do 0 minus v squared, I'll end up with y equals negative v squared. Okay. Look at the top. All right, what's happening along the top? Along the top here, the v values are equal to 1. The u values are increasing from 0 to 1. All right, so go back to my original equations. If x is equal to 2 times u times v, then x is equal to 2 times u times 1. And now, go along the right side. Okay. On the right side, u is equal to 1. So if I let u be 1, now my x's are equal to 2v, and my y's are equal to 1 minus v squared. Now, the goal is to find some relationship between x and y. And now is where we get to make an educated guess. Oh, it would probably help my case if I finished out that one on the top. If x is equal to 2u, then what is my y? My y is equal to u squared minus 1. All right, so now I got this u squared minus 1 over here for y, and I got a u squared over y. How are the two things related to each other? Let's make a guess. What if I took what if I took this guy over here? I think that might give us a better idea. So now we have to find some relationship between the x's and the y's. So start with this row across the top because I think that's the most promising. I end up with an x equals 2u and a y equals u squared minus 1. What can I do to get those things equal to each other? Well, the first thought would be square the left-hand side so at least we get things that are squared. All right, so let's square that x squared. So now on the left side, I got 4u squared. On the right side, I've got u squared minus 1. All right, so maybe I should multiply by 4. So I multiply by 4, and I get 4u squared minus 4. But they're not quite equal to each other yet because I got an extra 4 on the right-hand side. So let's add a 4. So add a 4 over here, add a 4 over here. Now they're equal to each other. So the first equation is x squared equals 4y plus 4. This is one of the original xy boundaries. All right. What's the other boundary? Well, let's take a look at the v's. We just dealt with u's. Let's deal with v's. What set of v's connect both x's and y's? The first two do not, right? The first ones have zeros in them. So it looks like this set over here connects x's and y's. So there's got to be some relationship between the 2v and the 1 minus v squared. Well, maybe I'll use the same trick as I had last time. Square the left side. So that 2v was my x. We're going to square that. The 1 minus v squared is my y. So now I've got 4v squared and a 1 minus v squared on the other side. Well, maybe I should multiply the right-hand side by negative 4. Maybe that'll help me. So I'll multiply that y by negative 4. And I get what? 4v squared equals 4v squared minus 4. So if I add a plus 4, it looks like it solves everything. And so the other equation, the other boundary, is right up top here. It's x squared equals negative 4y plus 4. All right, what's the important takeaway from this? The important takeaway is that you had some boundary on the bottom of this and the top. They were both x squared functions, right? X squared equals 4y plus 4, x squared equals negative 4y plus 4. They were the original boundaries. If you apply this transformation, you no longer have to integrate from the one curve to the other curve. You now only have to integrate from 0 to 1 on the u's and 0 to 1 on the v's. So it should make the calculations a whole lot easier. All right, I'm going to do a series, I guess, of shorter videos. So this was your little introduction. We're going to work on the Jacobian next.